Here's a bug that's easy to write and surprisingly hard to notice until production hits it. You create a database module. It exports a DB object with a query method. Inside the module, you call db.connect to establish the connection. Then somewhere in your app startup code, you import that module and immediately call db.query in the very next line. What happens? The query fails. The connection hasn't been established yet. db.connect is asynchronous. It returned immediately, started establishing the connection in the background, and your code kept running. By the time db.query is called, the connection is still pending. This is the asynchronous initialization problem, and it's a category of bugs that can silently corrupt your application if you're not careful. Unlike a crash that's obvious, this bug might only manifest under specific timing conditions, during startup, on slow databases, or when the connection pool needs to warm up. In development it might work fine. In production with a remote database it fails every time. The book identifies 3 distinct solutions, each with different trade-offs. And understanding which one to use in which situation is the kind of judgment that separates senior engineers from junior ones. The naive solution is to add a check inside every function. If not connected, throw an error. This is local initialization checking. It's explicit, it gives good error messages, but it's verbose. Every single database function needs the same guard. If you forget to add it somewhere, you have a silent bug. Scale this to a module with 20 methods and the pattern becomes error-prone maintenance overhead. There must be better approaches. And there are 2, each elegant in a different way. The simplest fix to the asynchronous initialization problem is to not start your application until all components are ready. This is the delayed startup pattern, and it's exactly as straightforward as it sounds. Instead of your application server starting and immediately accepting requests, you wait. The startup sequence becomes, initialize all async components first, await their initialization promises, then start listening for connections. Your database connects, your cache warms up, your message queue connects, all before the first request can arrive. The code pattern uses async/await at the top level. Your main function awaits db.connect, then awaits cache.connect, then calls applisten. Nothing runs until everything is ready. This approach has real appeal. It's honest about dependencies. The app literally cannot start without its dependencies being ready. It fails fast. If the database isn't reachable at startup, the application crashes immediately with a clear error instead of starting up and then failing on the first query. Operations teams appreciate this. A service that fails to start is obvious. A service that starts but silently fails on first use is subtle and dangerous. The limitation is also obvious. Your entire application is unavailable during initialization. For most web services this is acceptable. The startup phase is brief, measured in seconds. For high availability systems with zero downtime requirements, it matters more. And there's a practical edge case. What if your database goes down after startup? The delayed startup pattern doesn't help with reconnection. You'd need separate reconnection logic for that. This is where the third pattern, pre-initialization queues, turns out to be more comprehensive. The most elegant solution to the asynchronous initialization problem is to not block anything, not fail, and not require callers to know about initialization state at all. You achieve this through pre-initialization queues. Here's the idea. Your module maintains an internal queue. When a caller invokes a method, say db.query, SQL, the module checks if initialization is complete. If it is, execute normally. If it isn't, push the call and its arguments onto the queue and return a promise. Internally, once initialization completes, you drain the queue, execute every buffered call in order with its original arguments. The callers who called early get their results back through the promises they received. The callers who called after initialization don't even know anything happened differently. From the outside, this module looks like a normal synchronous-ish module. You call it. You get a promise back. You don't know or care whether the call was executed immediately or buffered and replayed after initialization. The module hides the complexity entirely. This is the pattern many database drivers actually implement. If you've ever used a MongoDB driver and wondered why you can call collection.find before the connection promise resolves and it still works, this is why. The driver maintains an internal operation queue during the connection phase. The pattern maps cleanly to a design principle the book emphasizes throughout: hide complexity behind clean interfaces. The caller's code shouldn't need to know about the module's lifecycle. A well-designed module handles its own internal states and exposes a consistent interface regardless of those states. The cost is slightly more complex module internals. The benefit is that callers are completely decoupled from initialization timing, which means less coupling, less coordination, and fewer classes of bugs. Now that you understand all three approaches, let's be explicit about when each one makes sense, because the choice has real consequences on your system's architecture. Local initialization checks are the right choice when you need fine-grained error handling at the call site. If different callers need to handle uninitialized state differently, maybe some can retry, some can fall back, some should abort, then explicit checks give you that control. The cost is verbosity and the maintenance risk of forgetting a check. Delayed startup is right when your application genuinely cannot function without all its dependencies ready, and fast fail behavior is a feature. An API server that needs a database for every request is a good candidate. The application start sequence becomes self-documenting. You can read exactly what must be ready before the server accepts traffic. Operations teams can tell at a glance what your application depends on. Pre-initialization queues are right when you want maximum flexibility and minimal coupling. They're ideal for modules that might be used early in the application lifecycle before their own async setup is complete. They're also the right pattern when you want your module to handle reconnection transparently. The queue behavior during reconnect is the same as during initial connect. There's a fourth consideration the book touches on: what happens in serverless functions, where there's no persistent connection. The initialization problem reappears in a new form. Each function invocation may or may not have a warm database connection. Cloud-native architectures have evolved specific patterns for this, but they all trace back to the same fundamental question: how do you call async code safely before you know it's ready? Understanding these three patterns puts you in a position to answer that question thoughtfully in any environment.